Hello, everyone. Thanks for joining today's session. A warm welcome to you all. My name is Noor, and I'm the product manager for electromagnetic applications here at SimScale. My focus is on making electromagnetic simulation accessible to engineers to help them innovate faster. And here's what we'll cover today. After this introduction, I'll be sharing how we at SimScale empower organizations through cloud-native multiple physics simulation. And next, I'll be presenting a live demo where I will showcase a design study using electromagnetic, thermal, and flow analysis. And we'll be using same model for all these analysis types, but of course, we will be focusing on answers of different physics. And finally, we'll have a Q&A session where I will be happy to address your questions. But one thing I would like to note here is please feel free to write your questions already. I will be going through them at the very end. So before diving deep into the demo, here's a quick introduction to SimScale as a company, especially for the ones that not have heard about us before. Let's first talk about why we are working on our cloud-native engineering simulation platform. Our mission is to empower engineering teams to innovate faster, and we are doing this by making engineering simulation truly accessible at any scale. So this means first, the engineering simulation to be truly accessible at any place and at any time. And this covers the data that is available to engineers in your organization to be able to judge the results, but also being available to the experts at SimScale. And our live support that we provide is very important to our platform. And we've been actually recently rated by G2 as the easiest to use simulation and CAE software. And you can see some of our customer logos that already use SimScale and are supported by our support team to reach their simulation goals. And here, let's get more insights about the cloud-native nature of our platform. I already mentioned our live support and how important it is to us. So support is done very differently on SimScale compared to the traditional simulation tools where we need to file a support ticket and then you wait to hear from the simulation provider for days, if not weeks. And what we do instead is our support team is engaging with the customer problem at the moment of our customers facing that problem, not later. Therefore, you can reach out to our live support anytime, and you can even collaborate on the project together. And also, we deliver simulation at any scale, which means you can run simulations at any instance. So this actually means both two things. First, you can pick more resources for your complex or let's say time-dependent and computationally more demanding cases to make them run faster. Or second, you can also start unlimited number of simulations in parallel. And then you can create a design optimization study with these simulations or use the results for a system level simulation, or you can create a reduced order model. But also you can use large number of simulation results for AI training. And I already mentioned the broad physics aspect, which is also the topic of today's webinar actually, which gives the engineers to work with multiple physics in a single platform. And additionally, the cloud-native aspect provides the user the independence to run simulations anytime and anywhere without any limiting factors such as the remote connection requirements or being in the office, etc. And you can adapt cloud-native simulation just as you wish. For example, you can start with one team and then make it available to more teams or for the whole organization, just as you wish. And therefore, both the accessibility of the simulation and also the data storage aspects of cloud-native engineering simulation is giving us a prime position to be a good fit for AI predicted physics as well. So what we provide in the platform is running the partial differential equations in parallel. And the moment these simulations are completed, then actually they're ready for AI training. So you do not need to worry about number of simulations you need to start, because you can run all of them in parallel. But also you don't need to worry about importing any simulation results or data to SimScale, because your simulation data is immediately ready to be utilized for an AI training. You just need to decide now or later, so as you wish. And soon we'll be diving into a live demo where I'll be demonstrating how we can leverage cloud-native simulation platform and what it truly means to have all physics accessible within a single environment. And we'll be exploring a cloud-native multiple physics simulation for a solenoid valve example. So the solenoid valves are compact and high-precision components, and they sit at the intersection of electromagnetics and heat transfer and also fluid dynamics. And their performance relies on how efficiently the coil can generate the magnetic force, and also how well the heat could be dissipated during actuation, and how smoothly the coolant is flowing through the valve body. And in this session, we'll see how cloud-native simulation can help us to explore these physics so that you can eliminate the silos of traditional tools, and you can make fast design decisions because you are using one single platform and have access to multiple physics. And to bring the scenario to life, let's first take a look at a real-world example. So, as I said, a coolant switch valve used in electric vehicles is today's application. And here in the slide, you can see the valve shown in two states. On the left, it's in the open position, so it's allowing the coolant to flow freely through the system. And on the right, it's closed, so it's blocking the flow. And the key components are highlighted here. So we see the housing, which is providing some mechanical support, and it's also covering the important components of the solenoid valve. And we see also the solenoid bushing, which is guiding the moving plunger. And we see the coil inside the housing. So that's the part that is generating the magnetic field that is necessary for actuation. And we see also the plunger, the component that is moving up or down to open or close the valve. And finally, we see the valve body where the coolant is physically flowing within. And in this case, our coil is a voltage excited coil, but it can be also a current excited coil. Therefore, when a voltage is applied to the coil, it's producing a magnetic field that is moving the plunger downward as we start from the open position, and then it's closing the valve. And this sounds like a simple movement, but in reality, it involves electromagnetic actuation, the heat generation due to the electrical losses, and also fluid dynamics because the valve is regulating the coolant flow. And all of these physics should work together seamlessly for optimal performance. And here on this slide, we break down the three main physics perspectives we'll be exploring today for the solenoid valve design. So they are electromagnetics, thermal, and flow analysis. And each is critical for reliable operation in real-world EV systems. So let's start with electromagnetics. And so the heart of the solenoid's function is converting electrical energy into mechanical motion. And we need to focus on two key questions from electromagnetics perspective. So First, how much force is generated to move the plunger reliably, and how quickly does this force is building up after the voltage is applied. Because in EV cooling systems, the rapid and dependable valve switching is crucial for battery thermal management. So early electromagnetic analysis can ensure you to ensure that performance targets are met. And in the thermal simulation, the driving current through the coil is generating unavoidable resistive heating. And in compact in EV environments, it's not likely to have active cooling systems. So the solenoids rely on natural convection to dissipate this excessive heat. And we'll be predicting temperature rise by using ohmic losses from electromagnetics as inputs to thermal simulation in our application today. And that can help us to answer whether the coil is overheating. And we can also have early thermal checks because it's essential to ensure the long-term reliability of this component. And finally, once the valve is switching, the coolant must flow through the body with minimal pressure loss, because high pressure drops would be forcing the pump to work harder, and that reduces EV efficiency and its range. And we'll explore multiple flow rate scenarios, and we'll be checking pressure drop performance to identify any design bottlenecks early so the valve can support optimal thermal system efficiency. And when we combine all three physics in a single cloud-native platform, we can accelerate this design validation process. We can find, we can uncover the interactions across the domains, and we can iterate on our designs fast. So to show this live in the platform, I will be leaving my presentation and I will go to the platform directly. So to start simulating, all you need to do is you need to go to SimScale website, and then when you click on your profile, you end up at the dashboard. So what dashboard shows us is the projects we are working on, and not only the projects you're working on your own, but also the projects that are shared by your teammates, so you can collaborate easily. And on the left-hand side, what I see is, for example, I'm part of the SimScale organization, and I can see my teammates, and I can also check the analytics to have an idea about what is my simulation usage. So here's the coolant control solenoid valve is today's project, and it's already open here. So what we see here is the full model. But one thing to note is not for all the analysis types, I need the full model itself. For example, if I would like to run a fluid flow simulation, then of course I don't need the solid parts. In that case, what I need to do is very easy. So I need to define the internal flow region in my simulation so that when I'm running the flow simulation, I don't use the solid parts. And as you can see, my flow region is already generated, which means that I don't need the solid parts anymore to run a flow simulation. So I just save, and now my model is ready to run a flow simulation on. Now let's check how the model looks like for an electromagnetic analysis. As we can see, there's the air region surrounding the solid parts. And one thing to note here is I don't have my valve body because it's not electromagnetically important component. Therefore, I just left the important and related components for my electromagnetic analysis due to their material properties. So let's say I would like to now create a simulation. What you see here is what I mean by one platform and multiple physics, because you see the simulation panel where you can pick from the physics different analysis types. And here, as my first simulation, I pick electromagnetic analysis. And I already had a simulation created here, so I will be following that. And as you can see, I picked the model within my electromagnetic analysis as time transient because I would like to run a transient simulation today. And what you'll see here is a simulation tree. So it's actually a very easy workflow because it's directing the user for the steps to be followed. It's very intuitive. And what I see here is I created a copper material, but I didn't assign any bodies. That's why it's showing me red. So my copper will be the two coil parts I have here. So I easily assign them. And then I have the stainless steel rated here. One thing I would like to notice, so for this stainless steel, I will be assigning the plunger. And here, as you can see, the magnetic permeability type is selected as constant. But I also have the option to define it nonlinear by defining a BH curve. And how you can make use of this is you can bring your own BH curve, and then that will be taken into account. And also, another point I would like to mention is we have an extensive material library for our electromagnetic analysis. So, for example, if you go to one type of steel here, you'll also see the BH curves already being provided. So it's very easy to pick also from the material library and then go with your simulation setup. As the next step, I will be assigning my coils. As I already introduced, it's a voltage excited coil, and I have the option to pick the topology either as closed or open. And in this case, it's a closed coil because there are two bodies and they're sharing one internal port within, and that internal port will be the phase where I'm assigning this excitation either as voltage or current. So I picked two bodies, and by default at SimScale, the phase you're selecting for the internal port is inwards. So when I select this phase for my internal port, it makes sense when I think of plunger direction and the magnetic field generation. So the coil assignment is already done as well because I have a single coil. And one last thing, I also would like to assign a result control item because I'm interested in the force generation on my plunger. That's why I will be picking the plunger and I assign result control item on it. So now it's ready to go. What I would like to also show is we also talked about thermal simulation. So when I finish my analysis, I will here show the finished analysis. This is a transient simulation, and we see the ohmic loss distribution right now, and we are at the very last step. So in order to run a thermal simulation, I am interested in seeing the ohmic losses on my coil because that will be the power source for my thermal simulation. So here I see the integral value on this volume, on these two volumes actually, because the coil is split. And all I need to do is I have my thermal simulation here. And as you can see, again, I assigned all the material properties and I go to my advanced concepts. And here I have the option to assign power source. And here all I need to do is picking coil and then assigning this value I got from my electromagnetic simulation. And that's all for my thermal simulation setup as well. Okay, now I will go back to my slides to talk a bit more about my the results of my analysis. So now that we've seen how to set up and run the simulations in the cloud, Let's take a look at some of the important results we obtained across different physics domains. First, starting with electromagnetics. Here I'm showing a graph of the force generated in the downward direction, because that was the direction needed to move the plunger and close the valve, and it's plotted against time. And along with that, we also see the coil current over time. Since the coil was voltage excited, we can easily see that the current density is building up over time, and force generation is also following a similar pattern. And this allows us to understand two critical design metrics. It's showing us first how fast we can achieve the minimum required force to start the valve actuation, and second, how efficiently the excitation system behaves. So it means how quickly the magnetic field is building up and reaching the functional levels. And in real-world applications, the faster actuation can mean quicker valve response times. And we said that this is a EV component, and that's directly impacting cooling performance regulation in EVs. And thanks to cloud native simulation, we can also easily adjust design parameters like the coil turns or the core materials or the excitation voltage or current values. And we can immediately test different scenarios without waiting days for setups for solving. And let's move on to thermal simulation results. So we use the ohmic losses computed from the electromagnetic simulation, and we assigned these losses as power source to the coil in the thermal simulation setup. And because this is still an early stage design scenario, I chose the immersed boundary method within my thermal simulation analysis types, rather than dealing with a body fitted mesh, because this approach is allowing me to quickly iterate on the thermal behavior without needing to do any CAD cleaning or having my model ready for simulation. And this is a major time saver for initial exploration and optimization of my design. And for the cooling condition, I ran a natural convection simulation, meaning there is no forced airflow, and that's realistically matching how solenoid valves are operating inside EVs in real life as well, because they don't have dedicated cooling fans or systems. And from the results, what we see is the maximum temperature is reached in the coil, around 45 degrees. And we can also see the temperature distribution across the full assembly. And these insights are crucial to ensure that the valve won't be overheating during operation. So whether it can maintain reliable performance without risking the materials within, or for example, the magnetic performance degradation. And finally, let's take a look at the internal flow behavior through the valve. Here we set up a parametric flow experiment and 8 simulations in parallel took place, each with a different inlet flow rate. And again, thanks to cloud native simulation, these all completed very quickly without needing to queue them one after another. And the main output we're interested in here is the flow rate versus pressure drop curve. And this relationship is important in a coolant control solenoid valve because excessive pressure drop across the valve would be increasing the load on the EV's cooling pump, and that demands more power and ultimately reducing vehicle efficiency. And by analyzing how the pressure drop behaves across different flow rates as early as possible in the design stage, of course, we can have some fine-tuning in the internal geometry, such as in the flow channels or any shape or the valve openings. So to minimize energy losses and ensuring a reliable coolant delivery and optimizing the overall thermal management system. So in summary, today we saw how electromagnetics, thermal behavior, and fluid flow all interact in the performance of a single solenoid valve. And with all these three types, electromagnetics, thermal, and flow, they were all simulated in one cloud-native environment. And by making use of that, you can quickly understand how design decisions are having an impact on multiple physics. You can spot the design bottlenecks as early as possible and iterate fast without traditional simulation silos slowing you down. Thank you very much for your time and interest. And now I'm really happy to answer the questions as best as I can. Okay, so we have a couple of questions. I will be starting with whether simulations can be done in local PC and cloud also if needed. That's an interesting and very good question. So you should, maybe I should remind you that SimScale is a cloud native tool. So you don't have the option to run or utilize it on your local computer. All you need is an account, and then you can start simulating, and you have access to high performance computing. But this is only in the cloud, so you don't download anything and you don't have the chance to use your own local resources. Hope that answers it. And another question is, you've shown how fast the magnetic field builds up and when the minimum force is achieved, but what about the actual movement of the plunger? Can this motion be simulated too? That's also a very great question, because what we see is motion is important part of electromagnetic simulations, either if it's electric motor or applications such as solenoids where translational motion is happening. So what we've shown today, or what we saw today, is the static force build-up scenario. So it's the moment just before the motion begins. But I agree, yes, with motion-coupled simulations, we can track the plunger's real-time displacement in time, and we can also, and we do this by assigning a velocity, or we can even take kinematics into account. And this is a capability that we're working on right now as well, and soon will be available in our platform. And actually, I'm glad this question was asked. If you are interested in getting early access when this capability is ready, and if you like to test it directly, please reach out. Another question is, what if I want to change the coil geometry or materials? Then how easy is it to rerun everything? So the answer to this question is that is very easy, because that's one of the key benefits of a cloud native simulation as well. So once your setup is ready, and either if you already run some simulations or you're planning to run, you can clone your design. So you can copy your simulation and then tweak material properties or geometry and start your simulations in parallel. So you don't need to rebuild anything from scratch, or you don't need to wait for long solve times locally as well. And I'm also checking time, so maybe a few more minutes to answer a few more questions. And another question is this finite element method simulation or employing other methodology? So it depends on which type of physics you're interested in and which analysis type you're going with, because what we're trying to always achieve is every problem might be a very good fit for different analysis types. So for structural, for flow, for electromagnetics, depending on what would be the good fit, we have multiple. And yes, finite element method is one of them, but also we have a finite volume method, or other types of methods as well, wherever it's a good fit. But for electromagnetics, yes, it's finite element based. And the last question, how can I start simulating if I do not need to download anything or set anything in my local computer? We talked about this a bit as well. So all you need is actually a web browser and an internet connection. So you just need to go to platform and have an account and log in to start simulating. So you upload your CAD and that's all you need to do. And everything from meshing to solving to post-processing is happening in the cloud in one single platform. And you can easily collaborate with your teammates as well. I see more questions coming. I will be writing back to you with the answers, but thank you very much for your interest. And if you have any questions, here is our contact details, and you can also reach out to us through the live support anytime you wish. And thanks for listening. I'm wishing you a great day.